Some missions slip into the world like a whispered memo, and others arrive like a parade with brass bands and blazing spotlights. Europa Clipper is neither of those, really. It is not a single moment of arrival, and it's not a single destination you can circle on a map and declare finished. Nor is it a landing or a drill biting into ice. And it's not a flag or a single photograph or a quick triumphant goodbye. It is a working rhythm, a spacecraft that lives by restraint as much as by action, by the quiet discipline of limits, power, temperature, pointing, data storage, radiation, kept in balance while it moves through a place where balance is hard to hold. Because Jupiter is not gentle. Jupiter is bright and enormous and far away, and its magnetic environment can be harsh enough to damage electronics the way salt air can corrode metal, only faster, and with physics that does not care whether you are ready. Europa sits inside that environment, moving through it like a pale stone in a fast river. So Europa Clipper does something that feels, to me, like careful work rather than heroic drama. It does not move in. It passes by. Again and again, it returns to the scene at a precise time, on a precise path, for a brief window when the evidence is closest and the instruments can see what they need to see. Then it retreats. It pulls back into safer distance. It downlinks what it collected. It recharges. It corrects its orbit. It checks its own health. And then, when the geometry is right and the schedule comes due, it returns for another pass. 49 times. Not one grand gesture, but a long, patient sequence of flybys. A loop of motion, a calm arc around a giant world, and a steady return to the same questions. Is ice thicker in certain areas when compared to others? Are surface compositions telling the same story in this region as it does in the next? Is there warmth where we'd expect it to be cold? Is the magnetic signal consistent with a salty ocean beneath the ice? Can we detect any movement, cracking, shifting, venting right now? And so tonight, we will follow the evidence gently, one calm detail at a time. Back in my office, a quiet mechanical murmur holds the air together. It's the kind of background sound you stop noticing until it goes quiet, like the soft work of a fan or the distant city breathing beyond the glass. The desk lamp makes a warm pool of light across a folder labelled Europa Clipper, the kind of label that doesn't promise spectacle, just steady work that has to continue. The office, tonight, feels like a metaphor for the mission, a place built for repeat visits, a place where the most important moments are brief and scheduled, and everything in between is preparation and balance. A notebook that has to stay dry, a lamp that has to stay on, a small system of power, temperature, and time, managed so the next pass can happen cleanly. Europa Clipper is an orbital routine, an instrument suite, and a promise of careful measurement, returning to the same moon from different angles, different altitudes, different lighting, until the scattered clues begin to line up. My name is Madeline Rowe, and this is the science of the Europa Clipper for sleep. If you're listening in bed, let the room settle around you. Let the edges soften. You don't need to hold every acronym. You don't need to memorize every number. All you need to do is follow the case file as it opens page by page with a calm hand. We'll start with the reason Europa is on the list at all. Europa does not look, at first glance, like a place that should matter this much. It's a moon, not a planet, a smaller world, an icy one. From far away, it can seem smooth and pale, bright enough that it reflects sunlight well, like a bead of frost in the dark. But the story of Europa is not written on its surface alone. It's written in what the surface suggests is happening underneath. An ocean world is a particular kind of hypothesis. It's not a claim that there is life. It's not a claim that there are fish under the ice or forests at the bottom or anything like that. It's a claim about structure, that beneath the ice shell there is a layer of liquid water, global in scale, and that this liquid has been there long enough and is connected enough to energy sources to be worth investigating as a potentially habitable environment. In planetary science, habitability is a careful word. It does not mean inhabited. It means the conditions could allow life as we know it. Liquid water, chemistry that can build complex molecules, energy gradients that can be used, and enough stability, enough time for those ingredients to matter. Europa, as best as we can tell from decades of observation, may have those ingredients in some combination. It almost certainly has water, and likely a great deal of it, locked beneath ice. The evidence for that comes from several lines, but one of the most famous is magnetic. Jupiter has a strong magnetic field. It rotates. That field changes in time at Europa's position as Europa moves through it. Conductive material responds to changing magnetic fields. It generates an induced magnetic signal, an echo in a sense that can be detected by a passing spacecraft. That echo is consistent with something salty and conductive beneath the ice. Not proof in the courtroom sense, but strong evidence in the scientific sense, because it fits the measurements and it fits the physics. Then there is the surface itself. Europa's surface is crisscrossed with long lines, fractures, ridges, bands. It has relatively few large impact craters compared with older, more inert surfaces. That tells us something about age and renewal. A surface that erases its scars is a surface that is being resurfaced by ice shifting, by material rising, by processes that are not dead. And then there are hints of chemistry, a reddish-brown material staining parts of the ice, suggesting salts or other compounds altered by radiation, mixed and transformed into something that stands out against the bright water ice. Europa is not only cold, it is active enough in its own slow way to keep a file open. So how did we get here? To the point where we send an entire spacecraft to pass a moon 49 times. The story begins, as these stories often do, with flybys. In the 1970s, Pioneer and then Voyager entered the Jovian system and gave us our first close looks at Jupiter's family of moons. The Voyagers showed that Europa's surface was strange, lined, cracked, not heavily cratered. The images were not just pretty, they were unsettling in the best scientific way because they suggested that Europa was not a simple frozen rock. Then, having launched in 1989 and arrived in 1995, Galileo changed the case file from curiosity to serious inquiry. Galileo performed multiple flybys. It measured the environment, it mapped the surface, and it provided that magnetic clue, evidence consistent with an ocean beneath the ice, perhaps containing more liquid water than all of Earth's oceans combined. That one sentence, more water than Earth, has a way of catching in the mind. Not because it means Europa is Earth-like, but because it means Europa may be an ocean world of staggering scale, hidden beneath a lid of ice. Since Galileo, other missions and telescopes have added pieces around the edges. Cassini, on its way to Saturn, swung by Jupiter and observed the system for months. New Horizons, on its way outward, took its own images. Hubble observed Europa in ultraviolet and reported evidence that could be consistent with intermittent water vapor plumes, possible jets that rise above the surface and fall back down. Later, reanalyses of Galileo data also suggested the spacecraft may have passed through something plume-like during a close encounter. None of that is a tidy, simple conclusion. It is a pattern of hints. And hints, when they come from multiple directions, are exactly the sort of thing that leads to a mission built to measure. Europa Clipper is designed to assess habitability, not to detect life. That distinction matters, and we'll keep returning to it because it keeps the story honest. Europa Clipper asks, what is the structure of Europa's ice shell and ocean? How does the ocean interact with the surface? What is the surface made of? How does the space environment alter it? And where is the moon most active right now? Those questions are answerable by instruments. So the next question in the file is, how do you safely and reliably gather that kind of data at Europa? And this is where the mission becomes, in a quiet way, elegant. Europa Clipper does not orbit Europa. Instead, it orbits Jupiter. It enters the Jovian system, settles into a looping orbit around the planet, and uses that orbit to stage repeated close flybys of Europa. Each flyby is a brief encounter, an intense window when Europa fills the instrument's fields of view, when the spacecraft sweeps past at close range, when the data pours in rapidly. Then the spacecraft spends most of its time away from Europa, in a higher, safer part of its Jupiter orbit. This does several things at once. It reduces time spent in the harshest radiation regions near Europa. It gives long spans of time to transmit data back to Earth. It allows the mission to vary geometry from flyby to flyby, different lighting, different surface regions, different angles, so that over dozens of encounters, the spacecraft can build global coverage. It is, in other words, a mission designed around repetition, like checking the same ledger every day from a slightly different angle until inconsistencies become clear and patterns emerge. The numbers are part of that rhythm. 49 planned close flybys, typical closest approach distances on the order of a few dozen kilometers to around 100, close enough that the instruments can resolve details, and that subtle signals in gravity and magnetism can be detected, but not so close that the spacecraft has to live in Europa's immediate neighbourhood all the time. If you like a timeline, we can lay it out gently. Europa Clipper launched in October 2024. It didn't go straight to Jupiter. Deep space travel is not only about distance, it is about energy, about shaping a path through the solar system using gravity assists, like borrowing momentum from planets without needing to carry endless propellant. So the spacecraft's crews included a Mars gravity assist in 2025 and an Earth gravity assist in 2026, each one a careful swing that changes the spacecraft's orbit around the Sun. Then, years later, Jupiter begins to loom large, not as a bright object in the sky, but as a gravitational well the spacecraft is falling into. In April 2030, Europa Clipper performs Jupiter orbit insertion. This is one of those phrases that sounds simple until you pause. Orbit insertion means you arrive with enough speed that Jupiter would fling you through and out again, unless you slow down. To slow down, you fire engines. You point the spacecraft in a way that allows a long burn, one designed and tested for exactly this purpose, and you trade propellant for a new status, captured. After that, the mission does not immediately begin 49 flybys the next morning. There is an arrival phase, there is orbit shaping, there is a process of settling in, calibrating, checking systems in the environment, adjusting trajectories so the tour can begin. And then, when the geometry is right, the flybys begin in earnest. The tour itself is its own kind of choreography. Between flybys, the spacecraft performs housekeeping tasks, orbit trims, battery charging, data transmission, and instrument maintenance, quiet work. the kind that never makes a headline but makes everything else possible. I like to linger here for a moment, because it tells you what kind of mission this is. Europa Clipper is not built around a single photograph. It is built around system health. It is built around instruments working in sync. It is built around repeated measurement, and those requirements shape the spacecraft itself. At Jupiter, sunlight is weaker than it is near Earth, much weaker. You can still use solar power, but you need a large collecting area. Europa Clipper carries large solar arrays, wide like wings, designed to gather enough light to run the spacecraft and its instruments at a distance where the sun is a smaller, colder presence. Those arrays are not just power sources, they are part of the spacecraft's geometry. They influence pointing constraints. They influence how the spacecraft turns during a flyby. They even host some of the radar antennas along their edges. Then there is thermal control. Space is cold, but spacecraft are not simply cold objects. They produce heat. Electronics produce heat. Batteries produce heat. Instruments produce heat. And the spacecraft is also exposed to sunlight and shadow and varying angles. So the spacecraft has to manage heat actively, moving it, radiating it away, keeping sensitive components within allowable ranges. It has radiators and thermal blankets and fluid loops and the quiet logic of mixing valves and set points. The aim is steady operation, not too hot, not too cold, not drifting out of tolerance. And then there is radiation. Jupiter's radiation belts are intense. The mission expects a large total ionizing dose over its lifetime. So Europa Clipper uses a combination of strategies: shielding, radiation-hardened components, thoughtful placement of sensitive electronics, and, perhaps most importantly, the tour design that keeps time near Europa brief. This is where the office metaphor returns. In a well-run office, you do not keep the safe open all day for no reason. You open it when you need it, you do the work, and you close it again. Europa Clipper, in its own way, treats the harshest environment like that. Dip in, collect evidence, pull back, preserve function. Now, if the spacecraft is the body of the mission, the instruments are its senses. Europa Clipper carries 9 primary science instruments, plus a gravity and radio science investigation that uses the spacecraft's telecommunications system. And one of the loveliest things about this mission is that the instruments are designed to work together, not as isolated gadgets, but as a coordinated team. During each flyby, the full array of instruments operates in sync, gathering layers of data that can be combined into a more complete picture. You can think of it like this. If you only had a camera, you would see shapes and colours, but not chemistry beneath the surface. If you only had a spectrometer, you would know composition, but not context. If you only had a magnetometer, you would infer an ocean, but not locate the most interesting places to study exchange. Europa Clipper brings the whole kit. Let's meet them gently, in groups, the way you might lay tools out on a desk. First, the instruments that look at Europa's surface in visible light. There is the Europa Imaging System, EIS, which includes cameras designed for wide-angle context and narrow-angle detail. With EIS, the mission can map surface morphology, study fractures, ridges, and bands, examine the shapes of features that suggest resurfacing or tectonic-like motion in ice, and create stereo coverage for topography. Topography matters because it is a record of forces, where ice has risen, where it has sunk, where it has been pulled apart. EIS also supports repeat imaging, looking at the same places on different flybys to check for changes. Not dramatic changes, necessarily. The kind of change that could be a new frost deposit, a shift in a plume deposit if such activity exists, a subtle alteration after a recent event. A detective does not only photograph the scene once, a detective returns. Next, the instruments that look at heat. There is the Europa Thermal Emission Imaging System, ETHEMIS, a thermal imager. Thermal maps can reveal where the surface is warmer than expected at night, or cooler than expected by day. They can help infer regolith properties, grain size, block abundance, how quickly the surface cools. They can locate heat flow anomalies, which could be related to internal processes. Thermal data is a quiet kind of evidence. It doesn't shout. It glows softly in the numbers. It tells you where to look closer. Then the instruments that read chemistry by reading light. There is MEIS, the Mapping Imaging Spectrometer for Europa, a shortwave infrared spectrometer. In infrared spectra, different compounds absorb light at different wavelengths. Hydrated salts, water ice, possible organics, and other materials all have spectral fingerprints. MEIS can map surface composition and chemistry at global scales and at regional scales. It can sample compositionally diagnostic properties of specific landforms. This matters because Europa's surface is not just ice. It is ice plus whatever has been delivered from space: dust, particles, implanted ions, and whatever has come from within if material has risen through cracks or been emplaced from below. MEIS helps distinguish regions, building a map of what is this place made of across a moon that may be actively exchanging material. And there is Europa UVS, the Europa Ultraviolet Spectrograph. Ultraviolet spectroscopy is a different window. It can map aspects of Europa's tenuous atmosphere, investigate vertical structure, and search for and characterize vapor if plume activity is present. It also helps study how the surface and atmosphere interact with Jupiter's magnetosphere, an environment that can sputter molecules off the ice and create a faint exosphere. Europa's atmosphere is not like Earth's. It is extremely thin, but it is still part of the case file, because it is what the spacecraft can sample directly during a flyby. Which brings us to the instruments that sample material in space near Europa. There is MASSPEX, the Mass Spectrometer for Planetary Exploration. MASSPEX is designed to measure neutral gases in Europa's environment, identifying major volatiles and resolving key organic compounds if present. If Europa is venting material, even intermittently, MASSPEX could detect chemical signatures in the gas environment near the surface. Even without plumes, the exosphere contains molecules that have been knocked free, created, or transported. Sampling that mixture can tell us about surface composition and processes. Then there is SUDA, the Surface Dust Analyzer. SUDA is a dust impact mass spectrometer. It measures the composition of dust grains that strike the instrument. Dust near Europa can include material sputtered off the surface, and possibly material related to active processes. By analysing dust composition, SUDA can provide another channel into surface chemistry, and potentially into subsurface chemistry if ocean-derived material is present in grains. Gas and dust are different messengers, and Europa Clipper listens to both. Now, to understand the ocean beneath the ice, the mission needs instruments that can sense what cannot be seen directly. This is where magnetism and plasma come in. There is ECM, the Europa Clipper magnetometer. ECM measures magnetic fields. Its key role is to characterize Europa's magnetic induction response to Jupiter's changing magnetic field. That induction response can constrain ocean properties, conductivity, and, in combination with other data, aspects of ocean and ice shell thickness. But there is a complication. Magnetic measurements in a plasma environment are not pure. They are influenced by charged particles, by currents, by the way the magnetosphere interacts with Europa's ionosphere. And for this, there is PIMS, the plasma instrument for magnetic sounding. PIMS measures the plasma environment, helping to characterize how plasma influences the observed magnetic fields, and helping separate induction signals from plasma-driven effects. ECM and PIMS work together. One measures the magnetic field, the other measures the charged particle environment that shapes it. This is how you keep the evidence clean. You do not take a single measurement and declare victory. You measure the context that might distort it, so you can correct and interpret. Then there is REASON, the radar for Europa assessment and sounding, ocean to near surface. Radar is one of the mission's headline tools because it can probe the ice shell. REASON operates in 2 frequency bands, one optimized for shallower sounding and one optimized for deeper sounding. Its design includes a VHF band centered around 60 MHz and an HF band centered around 9 MHz, each with its own bandwidth and wavelength characteristics. Radar signals travel through ice and reflect off interfaces, changes in composition, layers, pockets of brine, fractures, the boundary between ice and ocean if conditions allow. The exact penetration depth depends on many factors: ice temperature, impurities, roughness, attenuation, but the goal is clear: reveal structure inside the shell. REASON is not a drill, it is a sense of depth. It is how you map what is hidden without touching it. And then there is gravity and radio science, often shortened to GRS. This investigation uses the spacecraft's telecommunications system to measure subtle changes in the spacecraft's velocity during flybys, gravity pulls. If Europa's mass distribution is uneven, if there are variations in density, if there is an ocean that shifts tides, if the ice shell flexes, then the gravitational field will have signatures. By tracking the spacecraft precisely, scientists can infer aspects of Europa's interior. One of the key targets is the Love number, a measure of how much Europa deforms tidally. A deformable body is consistent with a global ocean layer beneath the ice. Again, not proof in isolation, but a strong line of evidence when combined with magnetics and geology. So these are the senses: cameras, thermal maps, spectrometers, ultraviolet measurements, gas and dust sampling, magnetism and plasma, radar sounding, and gravity tracking. In my office, this is the moment when the tools stop being a list and start becoming a method. Because a mission like Europa Clipper isn't just about having 9 instruments. It's about how you use them together, how you let one measurement steady another, how you turn a fast flyby into something that can hold still long enough to understand. I think of it as an evidence room. On one shelf, the photographs, crisp, detailed, full of texture. The ridges, the cracks, the long bands that look like the ice has been pulled apart and stitched back together. On another shelf, the thermal maps, a quieter kind of image where bright means warm. And warm can mean recent or rough, or simply different in the way it holds and releases heat. In a drawer, the spectra, not pictures of what Europa looks like, but fingerprints of what it's made of, wavelength by wavelength, turned into maps of ice, salts, and altered surface material. And then, in the corner, the measurements that don't look like images at all. A magnetometer's time series, a plasma instrument's counts and energies, a radargram, echoes returning with delay and strength, implying layers you can't see. A Doppler curve from the radio link back to Earth, so precise it can tell you when gravity has tugged the spacecraft just slightly off its expected line. If you've never looked at mission data, it's easy to imagine it arrives already shaped like a beautiful map, neatly labelled. But most of it arrives as raw sensation. A stream of numbers that only becomes a place after calibration, after correction, after careful alignment with geometry and time. Each flyby has its own posture. The spacecraft is moving fast. Europa is moving. Jupiter's magnetosphere is moving. The lighting is different. The angle is different. The distance is different. So the first act, after a flyby, is always the same. You make sure you know where you were and exactly how you were oriented. There's a kind of comfort in that. Before you interpret, you verify. You check the spacecraft's trajectory. You refine the pointing history. You confirm timing. You reconcile the clock that stamped the data with the geometry that explains what the instruments were actually looking at in each moment. You take the mess of a fast encounter and you pin it to a coordinate system that doesn't drift. Only then does the evidence start to stack. Images become mosaics, not one frame, but a stitched surface, overlapping, corrected, mapped. Thermal measurements become grids you can compare. This patch at night versus that patch at night. This region under one season of sunlight versus the next. Spectral cubes become composition maps, not just dark and bright, but this absorption feature is stronger here. This mixture is more likely there. And the beauty of 49 flybys is that you don't have to trust a single pass. A single observation can be a trick of angle or noise or lighting. But if a thermal anomaly repeats, if it shows up again when the geometry is different, then it starts to feel like a real feature of the moon, not a coincidence. If a spectral signature appears consistently over the same terrain, you begin to believe it belongs to the surface, not the measurement. Repetition turns suspicion into constraint. And constraint is the honest currency of missions like this. Europa Clipper may not hand you a single definitive number for the ice thickness everywhere, like a ruler pressed against the shell. What it can do is tighten the space of possibilities. It can tell you, in this region, the radar echoes suggest layered structure down to a certain depth. In that region, the gravity signal and the surface topography hint at a shell that flexes in a particular way. In another region, the magnetic induction response is consistent with an ocean of a certain conductivity, saltier or fresher, within a range, when you account for the plasma environment measured at the same time. It's like building a portrait from overlapping shadows. No single shadow tells you everything, but many shadows, cast from many angles, start to reveal the shape. This is why the mission's coordination matters. The instruments aren't just coexisting on the same spacecraft. They're designed to observe together, so that the data can be combined without guesswork about whether two measurements describe the same moment, the same place, the same conditions. When the thermal imager sees a warmer patch, the cameras see the texture there. The spectrometer sees what the surface chemistry looks like in that same patch. Radar may sound beneath it on a later pass. The magnetometer and plasma instrument describe the environment that could affect near-surface processes. And if, on some rare flyby, there is a hint of vapor, something that looks like a plume signature in ultraviolet, then the gas and dust instruments are already listening, already sampling, already ready to compare. It's not romance, it's procedure. The kind of procedure that keeps you from fooling yourself. There's another quiet truth here too. Europa Clipper's science is as much about choosing what not to say as it is about saying what you can. It will map, it will measure, it will constrain, and it will leave certain questions open on purpose, because that's what good evidence does. It doesn't fill every blank with certainty. It marks the blanks clearly, and then it builds the next mission's reason to exist. That's why I like the flyby tour design as a metaphor for the office. You don't solve the entire case in one night. You return with another angle, another measurement, another page of notes. You keep the system healthy so the work can continue. You keep the file tidy enough that when something finally clicks into place, you can see it without strain. And with that method in mind, with the evidence room stocked and the tools laid out in a way that makes sense, we can ask the next question in the folder. What are the mission's core objectives? Europa Clipper is organised around 3 major science objectives, and they form the backbone of the case file. The first objective is interior. Determine the thickness of Europa's icy shell and understand how the ocean interacts with the surface. This involves measuring ice thickness, looking for water within or beneath the shell, estimating ocean properties like salinity and volume, and characterising possible pathways of exchange. Exchange matters because habitability is not just about having water, it is about water and chemistry being able to meet. If the ocean is sealed away completely, then surface-derived oxidants produced by radiation might not reach it, and ocean-derived material might not reach the surface. If exchange occurs, then Europa becomes more dynamically interesting. The second objective is composition. Investigate Europa's composition, including surface and atmospheric chemistry, to determine whether the environment has the ingredients that could permit and sustain life. This includes mapping surface compounds, identifying salts and other non-ice materials, looking for organics and other building blocks, and understanding how radiation alters surface chemistry over time. The third objective is geology and activity. Characterize Europa's geology, how surface features formed, and search for signs of recent or current activity, including possible plumes, tectonic-like motion in the ice, and thermal anomalies. Geology is the record of processes. It is how you reconstruct what the moon has been doing, and what it may still be doing. These 3 objectives are not separate compartments. They overlap. A warm anomaly is a geology clue and an interior clue. A salt-rich region is a composition clue and an exchange clue. A magnetic induction signal is an ocean clue and a composition clue, because conductivity is tied to salt content. So the mission is designed to weave these threads together. Now, before we walk through a flyby, the mission's most soothing rhythm section, I want to slow down and talk about Europa as an environment. Because Europa is not just a moon with ice. Europa is a moon inside Jupiter's magnetic world. Jupiter's magnetosphere is vast. It is filled with charged particles captured and accelerated by the planet's rotation and magnetic field. These particles bombard Europa's surface, breaking molecules apart, altering chemistry, producing oxidants, and contributing to a thin atmosphere. This has 2 major effects on the case file. First, it means Europa's surface chemistry is constantly being modified. If you see a compound on the surface, you have to ask, did it come from within, from the ocean or the ice shell, or did it form because radiation rearranged molecules and implanted new ions? Second, it means the space environment itself is a dataset. PIMS measures plasma, ECM measures magnetic fields, Europa UVS measures aspects of the atmosphere, MASPEX samples gases. Europa Clipper is not only studying Europa's surface, it is studying the interface between Europa and space. This is important because exchange can occur not only through cracks and melt pockets, but through sputtering and atmosphere loss, through the cycling of molecules at the surface. And it is important because radiation complicates the interpretation. In a quiet way, Europa forces scientists to be careful. It's not enough to say, we detected this compound. You have to ask how it got there, how long it might last, what processes could mimic it. Europa Clipper's strength is that it does not rely on one instrument to tell the story. It collects overlapping evidence so that interpretations can be tested. Now, the part of the mission that I find the most sleep-friendly is the structure of a single flyby, because a flyby in this mission is a procedure. It has phases, it has pointing, it has instrument sequences, it has a logic that repeats. So let's walk through it like a quiet rehearsal. The spacecraft is in orbit around Jupiter. Europa is ahead on the path, a pale disk that grows slowly larger as the spacecraft approaches. Long before closest approach, the spacecraft is preparing. There are attitude changes, there are instrument warm-ups, there are checks that the pointing profile is correct. At very large distances, Europa is a small object in the field of view. Instruments that need global context can begin early. As the distance shrinks, tens of thousands of kilometers, Europa begins to fill more of the frame. Themis can begin a stare observation, capturing the full disk within its field of view, building a global thermal picture. Then, closer still, the spacecraft executes a carefully planned twist. This is where the mission's choreography becomes visible. Just prior to around 40,000 kilometers out, the spacecraft rotates about the nadir axis so that Suda and mass specs can face into the direction of motion, a configuration sometimes called nadir RAM. This matters because for a mass spectrometer and a dust analyzer, the direction of motion is the direction of sampling. You want the incoming flow. During this turn, the solar arrays also move to maintain good sunlight on the panels, while avoiding unwanted stray light into sensitive instruments. Everything is linked. Power and sampling and pointing are part of the same problem. At around 40,000 kilometers, as Europa fills the MEIS field of view, MEISA can collect its first global data cube, an infrared spectral map that will later be turned into composition. Then the spacecraft performs a slew across Europa that's coordinated among multiple instruments. This is sometimes referred to as a joint scan, a shared pointing motion that helps Themis, Europa UVS, EIS, narrow angle imaging, and MEIS meet their coverage requirements. It is one of the mission's defining moments of coordination, a single scan negotiated and designed so multiple instruments can get what they need without fighting for pointing time. This is how you build efficiency into a flyby that lasts only minutes at its closest. The spacecraft continues inward. Closest approach arrives the moment the spacecraft passes at its minimum altitude over Europa's surface. This is the peak of data collection. Imaging is sharpest. Thermal resolution is finest. Spectral maps have the best spatial detail. Radar sounding is at its most sensitive geometry. Magnetic and plasma measurements capture the local environment. And the gravity and radio science measurement is happening continuously, tracking how Europa's gravity perturbs the spacecraft's path. Then the spacecraft moves away. The sequence reverses in a way, but not exactly. There may be departure scans, occultation opportunities, depending on geometry, and continued sampling of gas and dust as the spacecraft exits. And then Europa shrinks again, becoming a disk, then a bead, then a point. The instruments wind down. The spacecraft returns to its safer orbital path around Jupiter, and the long, quiet interlude begins. Downlink. Europa Clipper gathers an enormous amount of data during a flyby, and it stores it on board. Then, over days, it transmits that data back to Earth through the deep space network. This is where patience lives. A flyby is fast. A downlink is slow. The mission is built to alternate between the two. And between flybys, there is housekeeping, orbit determination, small trajectory correction maneuvers, battery recharge, thermal management, and maintenance tasks that keep instruments healthy. Then the next flyby comes due, the same rhythm, with a new target region. Now, we can ask what the mission will learn from this rhythm. Start with the ice shell. Europa's ice shell thickness is not known precisely. Estimates vary, and thickness may vary regionally. Reason radar sounding will help map layering and potentially detect interfaces, pockets of liquid water within the ice, and the deeper ice-ocean boundary if conditions allow. EIS imaging and topography will map fractures, ridges, and bands that reveal how the shell has been deformed, resurfaced, and possibly cycled. Ethermis thermal maps can identify places where the shell may be warmer or where regolith properties differ, potentially indicating recent activity or variations in heat flow. Gravity and radio science can detect tidal deformation and infer interior structure and shell properties. Magnetometer induction measurements constrain ocean conductivity and, combined with other information, help constrain shell and ocean characteristics. The goal is not one number labelled ice thickness. The goal is a set of constraints that tell us how the shell behaves. Is it thick and rigid with little exchange? Is it thinner in certain regions? Does it contain shallow liquid reservoirs? Are there places where the ocean communicates more easily with the surface? Those are habitability questions, because habitability depends on exchange. Now, composition. Europa's surface is dominated by water ice, but it contains darker material, reddish streaks and patches that suggest non-ice constituents. MEES will map spectral signatures of salts and other compounds. EIS will provide colour and context. Europa UVS can help characterise atmospheric species and any plume vapour if present. Masspec samples, gases, and pseudosamples dust, providing direct compositional measurements in the local environment. Together, these data can help determine whether Europa's ocean and ice shell chemistry includes key ingredients, salts, volatiles, possibly organics, and importantly, the chemical gradients that could support metabolism if life were ever to exist there. Again, careful language. Europa Clipper is not a life detection mission. It is a mission that assesses whether Europa's environment could support life. Now, geology and activity. Europa's surface features are clues to ongoing processes: ridges, chaotic terrains, bands, possible subduction-like features, where surface plates might have moved, regions that look like broken ice refrozen in a jumble. EIS maps and classifies these terrains. ETHEMIS looks for thermal anomalies. Europa UVS searches for vapor signatures. Reason investigates internal structure beneath surface features. And the plasma and magnetic instruments help interpret how the environment interacts with Europa, which can be influenced by outgassing and ionospheric changes. One of the mission's quietly thrilling possibilities is that it might encounter plume material. If plumes exist and are active during a flyby, then Masspec and SUDA could sample that material, and Europa UVS could detect vapor signatures. But the mission does not depend on plumes. That's another important point. Plumes are intermittent and uncertain. They are not the foundation of the mission. They are an opportunity the mission is equipped to seize if it arises. Now let's widen the lens to the tour design itself, because this is where the mission becomes a slow unfolding. 49 flybys are not just 49 copies of the same event. They are distributed in geometry and longitude, designed to cover different regions of Europa under different lighting conditions, different local times, different distances, different observational goals. Some flybys prioritize low altitude for radar and imaging. Some prioritize specific regions suspected of being active or compositionally interesting. Some occur in daylight, some in night, enabling thermal measurements that rely on how the surface cools. And throughout, the spacecraft is balancing scientific ambition against radiation exposure and operational constraints. This is why the mission's Jupiter orbit strategy matters so much. In a Europa orbiting mission, the spacecraft would remain in Europa's environment continuously. That could increase data collection, but would subject the spacecraft to relentless radiation and limit downlink time. Europa Clipper chooses a different approach. Less time near Europa per orbit, more time for data transmission and safer operations, and enough flybys to build a global dataset. It is a mission designed to return more science per unit radiation dose. Now, in the case file, there is also a small human artifact tucked into the spacecraft, and it's worth pausing on, not because it changes the science, but because it changes the feeling of the mission. Europa Clipper carries a vault plate. It is placed within the spacecraft's vault area, attached to a metal plate, and it honours the mission's connection to Earth. It includes a poem by US poet laureate Ada Limon, etched in her handwriting. It includes designs that reference the Jovian system, and it includes something charmingly modern, a tiny silicon chip, fingernail-sized, etched with the names of more than 2.6 million people who signed up to send their names with the mission. There is also the phrase water, recorded in more than 100 languages, turned into waveforms and etched into the plate. A chorus of the same concept spoken by different mouths, turned into a physical pattern. When you think about Europa, a world where water may exist beneath ice for billions of years, sending the word water seems appropriate. It is not a message to Europa, exactly. It is a message about us. A note in a bottle, thrown into deep space, attached to a machine that measures. Now, we can fold in a module that often sits in the background of Europa stories: radiation chemistry. Europa's surface is constantly bombarded. Energetic particles break apart water molecules, creating reactive species. They can produce oxidants at the surface, molecules that, if delivered into an ocean environment, could contribute to chemical gradients. On Earth, gradients matter. They are what life uses. Differences in chemical potential, differences in redox state, differences that can be exploited. Europa's surface may be producing oxidants by radiation, while the ocean floor may be producing reductants by water-rock interaction. If there is a pathway for mixing, if surface oxidants can reach the ocean and ocean materials can reach the surface, then Europa's habitability potential increases. But if is doing a lot of work. The question is not only whether oxidants exist, but whether they can be transported downward through an ice shell that may be many kilometers thick. This is one reason geology matters. Features like chaos terrains and ridges may indicate regions where the shell is thinner or where exchange is more likely. It is one reason radar matters, detecting internal structures that might represent pathways. It is one reason composition mapping matters, identifying salts and other materials that might have risen from below. Europa Clipper's habitability assessment is, in part, an assessment of plumbing. How does Europa move material across its shell? Does it? Where? And how often? Another module that fits naturally here is the exploration history, because it shows how science moves by inference. Voyager images show lines and few craters, suggesting a young surface. Galileo magnetometer data suggests an ocean. Hubble ultraviolet observations suggest possible vapor. Reanalyses and models refine these hints. but none of these are complete by themselves. Europa Clipper is what happens when a field decides it has enough evidence to justify a dedicated investigation. Not a speculative leap, but a measured next step. Now let's talk briefly, quietly, about what Europa Clipper is not. It is not a lander. It is not a drill. It is not a sample return. It will not melt through ice. It will not look directly into the ocean. It will not carry a microscope searching for cells. So when the mission speaks about habitability, it is speaking about conditions, not about organisms. It is asking whether the environment below the ice could support life, based on what we can measure from orbiting flybys: ice thickness, ocean properties, surface chemistry, activity, and exchange pathways. That is, in itself, a profound step, because it takes Europa from a poetic idea, an ocean under ice, into a quantified environment with constraints. Now we can add another module: radar techniques. Radar sounding through ice is something we do on Earth, in Antarctica and Greenland, to map ice thickness and internal layers. Europa is not Earth, but the physics of radar, transmitting radio waves and measuring echoes, still applies. Reason uses 2 frequency bands because different frequencies interact differently with materials. Higher frequency, shorter wavelength, can offer finer resolution but may attenuate more quickly. Lower frequency, longer wavelength may penetrate deeper but with less detail. By combining bands, the instrument can target both shallow structure and deeper structure. Echoes can reveal layering. They can reveal changes in dielectric properties. They can detect interfaces that might correspond to brine lenses or boundaries. And in a best-case scenario, they can detect the ice-ocean interface itself. But radar data is not a photograph. It requires interpretation, it requires modelling, it requires calibration, it requires careful accounting for geometry and noise and scattering. Europa Clipper's repeated flybys help here too. Multiple passes over regions at different angles can help confirm whether features are real. Repetition is a kind of verification. Now let's bring in one more module: JUICE, the European Space Agency's Jupiter Icy Moons Explorer. JUICE has its own mission focus, with extensive study of Ganymede and the Jovian system. Its timeline and targets differ from Europa Clipper's, but the missions will overlap in the Jovian era. The value of mentioning JUICE here is not competition, it is context. Europa Clipper is focused on Europa's habitability assessment through repeated flybys. JUICE provides broader system science and deep study of other moons, including a future orbit around Ganymede. Together, these missions contribute to a fuller understanding of Jupiter's moon system, how these ocean worlds differ, how they are shaped by tides and magnetospheres, how they exchange materials, and how they might be habitable in different ways. But in tonight's folder, we stay with Europa Clipper, because the case file is already full. Now, if you're still with me, this is a good moment to return to the office metaphor, because it helps the mission's rhythm settle into something you can relax into. Europa Clipper is like an investigator who does not storm the scene and leave. It is an investigator who returns with a different tool each time. One day, the photograph. Another day, the thermal scan. Another day, the spectral map. Another day, the magnetic reading. Another day, a sample of air and dust. And each time, the investigator goes back to the office, files the evidence, writes notes, checks the tools, prepares for the next visit. That is the tour. And the tour is long enough that it changes the nature of what the mission can do. One flyby can be ambiguous. 49 flybys can reveal patterns. For example, if a region appears compositionally distinct in mass data on one flyby, the mission can target it again. If e-Themis detects a thermal anomaly, the mission can check whether it persists. If Europa UVS sees a hint of vapour, the mission can examine the context and look for correlated signals in mass specs and PIMs. If Reason detects a subsurface reflector, the mission can compare passes to confirm. Science becomes stronger when it can test itself. Europa Clipper is built to test. Now let's walk through the 3 objectives once more, but this time with a calmer, more narrative flow, as if we are leafing through pages. Page 1. The shell. An ice shell is not just a lid, it is a dynamic layer. It can flex under tides, it can crack, it can heal, it can convect slowly, like a thick, cold fluid, if conditions allow. It can contain pockets of brine and melt. It can be thin in some places and thick in others. To assess habitability, Europa Clipper needs to know the shell's behaviour. Reason asks, what is inside the shell? EIS asks, what has the shell done to the surface? e-Themis asks, where is the shell warm? Where does it cool quickly? Where does it hold heat? Gravity asks, how does the shell and interior deform? ECM asks, what is the conductive layer below doing? Together, these senses can constrain whether the shell allows exchange. Page 2. The ocean. An ocean under ice is not only water, it is salt water, most likely, because conductivity and chemistry suggest salts. Salinity matters because it affects freezing point, density, and electrical conductivity. It also matters for habitability because life uses ions, gradients, chemistry. Europa Clipper can infer ocean properties indirectly. Magnetic induction constrains conductivity. Gravity and tidal response constrain interior structure. Geology can suggest where the ocean interacts with the shell. And composition data can indicate whether ocean-derived salts have reached the surface. Page 3. The surface chemistry. Europa's surface is a laboratory of radiation. It is constantly being modified, producing oxidants and altering compounds. Composition mapping helps determine what is there now, but interpreting what is there requires understanding sources. Is a salt signature a surface radiation product, or is it a sign of ocean material? Is a dark region compositionally distinct, or is it simply rougher, affecting reflectance? This is where overlapping instruments matter again. You don't rely on one dataset, you combine. Page 4. Activity. If Europa is active, that activity might show up as fresh fractures, new deposits, thermal anomalies, or plume-like signatures. But activity can be subtle, so the mission looks for it in multiple ways. Repeat imaging searches for changes, thermal imaging searches for heat, ultraviolet spectroscopy searches for vapour, in situ sampling searches for compositional signatures in gas and dust. Plasma measurements can detect local changes that might accompany outgassing, and radar can look for shallow structures that might be associated with active regions. Page 5. Context. Europa is in Jupiter's system. Jupiter's magnetosphere shapes Europa's environment. So Europa Clipper measures the system as well. Magnetic fields, plasma, radiation effects. This helps interpret everything else. Now, if the case file were being closed as a report, this might be where we stop. But for sleep, we can let the story drift a little deeper into the procedural rhythm, because repetition is soothing. So let's revisit a flyby again, slower, as if we're watching it from the ground. The spacecraft is in its Jovian orbit, far from Europa, with its big solar arrays catching sunlight, its antenna turning toward Earth during downlink periods, its onboard systems maintaining thermal balance. Then the next encounter approaches in time, like an appointment. As Europa draws near, the spacecraft begins to point its instruments. Some instruments may take global observations early. The closer it gets, the more the pointing becomes choreographed. The thermal imager stares. The spectrometer collects its cubes. The cameras snap context frames, then narrow angle frames. The radar transmits and listens, with timing that has been simulated and tested. The magnetometer records continuously, but the data becomes especially valuable when the spacecraft is close enough that Europa's induced field and local currents are strongest. The plasma instrument measures the charged particles that flow around the Moon. The mass spectrometer samples neutral gases. The dust analyzer waits for impacts and reads their chemical story. And the radio system is doing double duty, keeping track of the spacecraft's motion for gravity science. Closest approach arrives, a moment that is both fast and dense. And then, just as quickly, it is gone. Europa recedes. The spacecraft begins to store what it gathered. It turns, eventually, to point its antenna at Earth. Data begins its slow journey home, across the dark. Days of downlink. Days when the mission is quiet. Not because nothing is happening, but because the happening is transmission. And then, again, orbit trims, checks, preparations. Then the next flyby. 49 times, this pattern. And because of that, the mission becomes less like a single trip and more like a steady practice. Now, there is one more piece of the mission that's worth resting on, because it's easy to miss amid the instruments and orbits. Europa Clipper is also an exercise in humility. It accepts that Europa is hard. It accepts that you cannot do everything at once. It accepts that the environment is hostile. So it chooses a strategy that maximizes the chance of sustained, high-quality measurement. It chooses a tour. It chooses a toolkit that overlaps. It chooses repeated flybys. And it chooses to ask questions that can be answered by those flybys. That is good science. Now, if you're drifting, you can let the next section be a soft recap, an accounting like closing a ledger. Europa Clipper's main science goal is to determine whether there are places below Europa's surface that could support life. It will do that by investigating interior, composition, and geology. It will orbit Jupiter and perform dozens of close flybys of Europa. It carries 9 instruments, plus gravity and radio science using telecom. It will map the ice shell and search for evidence of exchange. It will map surface chemistry and sample gases and dust. It will measure magnetic induction and plasma to constrain ocean properties. It will look for signs of activity, including possible plumes and thermal anomalies. And it will do all of this not as a single dramatic event, but as a patient series of returns. Now, let's take a final slow walk through the vault plate and the message, because it's a gentle way to close the file. A spacecraft is a machine built for measurement, but it is also a messenger of the species that built it. Europa Clipper carries the names of millions of people, etched into a tiny chip, tucked into the spacecraft's protective interior. It carries a poem etched into metal, a human response to the mystery of an ocean under ice. It carries the word water, spoken in many languages, turned into waveforms, sound made into shape, shape made into a traveling artifact. And then it travels, not to deliver the message, but to do the work, to return to Europa again and again with instruments that do not guess, but measure, to convert light into spectra, spectra into maps, to convert tiny gravitational tugs into interior models, to convert magnetic echoes into constraints on ocean conductivity, to convert dust impacts into chemistry, to convert thermal glow into clues about activity, to convert a cold, bright moon into a quantified environment. That's what it means in this folder to be bound to hard science. Not romance, though the romance is there if you want it, just evidence, layered, repeatable, constrained by physics. And if you like, you can let that be the feeling that settles into the room now. A calm sense of a distant world being approached with care. A sense of loops and returns, of brief encounters and long quiet intervals. Back in my office, the lamp is still warm. The folder is still open, but the pages have stopped turning. Outside the window is a dark slice of sky, and somewhere far beyond it, far beyond the small worries of a single night, Europa continues along its path around Jupiter, and Europa Clipper continues along its path around Jupiter as well, keeping to its schedule, keeping to its limits, returning again and again to gather what it can. If you're ready to sleep, you can let the mission keep running without you. You don't have to stay awake for the downlink. You don't have to count the flybys. The case file will still be there in the morning, neat and patient, full of careful measurements waiting to be read. For now, you can simply rest. And we can close the folder gently on Europa Clipper.